Hello and welcome to another episode of TWIML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this episode, we're joined by Hanbyul Joo, a PhD student in the Robotics Institute at Carnegie Mellon University. Han, who's on track to complete his thesis at the end of the year, is working on what is called the Panoptic Studio, a multi-dimension motion capture studio with over 500 camera sensors that are used to capture human body behavior and body language. While robotic and other artificially intelligent systems can interact with humans, Han's work focuses on understanding how humans interact and behave with one another so that we can teach AI-based systems to react to humans more naturally. In our conversation, we discuss his CVPR Best Student Paper Award winner, Total Capture, a 3D deformation model for tracking faces, hands, and bodies. Han also shares a complete overview of the Panoptic Studio, and we dig into the creation and performance of the models and much more. Okay, enjoy the show. All right, everyone. I am on the line with Hanbyul Joo. Hanbyul is a PhD student in robotics at Carnegie Mellon University. Han, welcome to This Week in Machine Learning and AI.
Thank you for having me today.
So you've been a PhD student at CMU since 2012, and the major focus of your work is in and around an environment that's been built there called the Panoptic Studio. What is the Panoptic Studio?
Yeah, so Panoptic Studio is basically a multi-view system with more than 500 camera sensors. And the system is also controlled by more than 50 machines. So this is indeed a giant system using computer vision technique to kind of measure or sense humans' body behaviors. So basically, we are very interested in the way we are using our bodies for social communication. For example, all these subtle facial expressions and body gestures and so on. And we really wanted to make a machine who can understand the body languages we are using. And in the end, we want to make a machine which can use these body languages to communicate with us. And for the purpose, the first thing we wanted to do is we want to collect this kind of motion capture data of naturally interacting people so that we can use some machine learning technique on top of that so that we, in the end, machine can understand these kind of signals. And that was the main motivation of this Panoptic Studio. And since we are interested in multiple people's interaction, to avoid all this complicated occlusion kind of problem, we wanted to make a system with many sensors, with many viewpoints, so that we can relieve these particular occlusion problems.
And this Panoptic Studio goes back quite a ways, it sounds like.
Yeah, so CMU has really amazing history on this multi-view system because Professor Takeo already started this multi-view system kind of research about, I think, 30 years ago. And at the moment, the major goal is to reconstruct 3D world, especially 3D object and 3D human body behavior. And to do that, obviously, this multi-view system is a really good kind of key to solve all this depth kind of ambiguity. At the moment, he already started this project with 15 machines, and it was extremely challenging problem at the moment. And our Panoptic Studio is kind of third generation, and our basic idea is, all right, maybe 40 or 50 cameras are already boring. Let's try to make a system with 1,000 cameras, for example, and see what we can solve. And that was kind of the beginning of our studio, and we particularly chose this social interaction analysis problem because that is indeed a challenging problem and a very important future problem so the machine can actually have a way to interact with us.
And so how do you frame out this social interaction problem, and what are the different research problems that come out of this broader problem?
So basically, you can easily consider natural language or verbal language problems. So, for example, nowadays there exists a very popular commercial AI system which can understand humans' voice and humans' language and use their languages to communicate with humans. But in that cases, the main channel is verbal language, which has sentence and grammar, all these rules. Basically, we wanted to do the similar thing with non-verbal languages. And for example, when humans are communicating each other, we use obviously our verbal languages, but we also use our facial expressions and our body languages. And all this subtle movement have some specific meaning, which is actually really hard to define, but humans are really easily understanding. And so basically, so maybe social signal understanding is something like expanding the dimension from just verbal channel to non-verbal channel as well. For example, the input can be, in this case, a verbal voice and also images or motion capture data. And machine understand the meaning of each sudden movement. And maybe machine can react to the input signals by using the similar output, for example, verbal language or non-verbal languages.
And so one of the papers that we wanted to talk about is a paper that recently won the CVPR Best Student Paper Award, and that was your Total Capture paper. And the full headline or the full title is Total Capture, a 3D deformation model for tracking faces, hands, and bodies, which is right in line with what you've been describing. Do you want to start, kind of jump into that paper, or do you want to tell us a little bit about where that paper fits into kind of the broader scope of research that you're doing for your PhD and at the studio?
Well, I think by explaining the paper, maybe the concept would be a little bit more clear.
Okay.
So basically, so let's say we are given a large-scale data set, and now we have some consensus that we can solve some problem using machine learning or this fancy deep learning techniques, right? So we have seen such kind of success in language part and computer vision or image processing part or object recognition part. And let's say we wanted to do the similar thing for body languages. The problem is the amount of data is extremely rare in these body languages. And maybe the first problem is what kind of data we can use for this purpose, for example. So machine sees the world, maybe using cameras, and how can understand the human's behavior. Maybe machine can use the images and videos directly for the purpose, similar to human, because actually we are using our two eyes, which capture the scene. And we can do all this visual kind of understanding part. And in the end, actually, we know the meaning of each sudden movement of humans. But using directly images or videos are extremely challenging because they are actually nothing to do with humans, but actually they are some pixels. And machine need to understand the meaning of all these pixels so that they can finally infer, oh, there is this human here. There is this human's arm here. Arm is moving such a way. I mean, solving all these problems from the image or video is extremely challenging problem. So although this is still a very popular area in computer vision, using such a data set for final output, meaning understanding the social interaction, is extremely challenging. So maybe another way to do that is just by collecting a lot of motion capture data, because motion capture is in a 3D space, and maybe that can be camera independent, illumination independent, and that each motion capture data, like for example, 3D skeleton, this already has some semantic meaning. We know where is the arm, where is the hand, how they are moving in 3D space.
And this is usually done with the humans are wearing specialized suits with I've seen pictures of these things. I don't know if they're balls or lights or sensors or something like that.
Yeah, exactly. So this area is extremely popular in movie industry and game industry, and these are main way to capture the real world human body signal so that we can put that to the virtual world. But our idea is to use such data for understanding human behavior using machine learning techniques. So to do that, we wanted to collect such kind of motion capture data a lot from naturally interacting people. The key here is, as you mentioned, we really don't want to use any artificial markers or suit because that may affect the natural motion of humans. For example, if you are wearing this kind of black suit and let's say you have all this sensor or all this kind of markers on your fingers, maybe your motion would be very kind of non-natural. We really wanted to avoid such kind of cases, and we just wanted to capture very natural human behavior when they are very naturally interacting. That means the method itself should be markerless. And this markerless motion capture area is also very popular in computer vision and computer graphics because if we can do the similar motion capture with a single camera or just multiple cameras, that can be really great to provide a 3D reconstruction output, or it can be also used for many, many purposes, like some action recognition, for example, or all this movie industry or game industry. But this itself is a challenging problem, and this is especially challenging if there are multiple people, because some part is extremely occluded, right? And our idea is, all right, we wanted to collect such data set first so that we can somehow tackle the final problem we are very interested in. But solving this problem itself is challenging. Then why not using a very kind of a good system which can reduce the challenge of this problem, so that we can start this project. And then if this is really meaningful, then actually we can expand the project to more challenging environments, such as in the wild, or maybe you can try to use some YouTube video for the similar purpose. So that was kind of the major kind of motivation of our Panoptic Studio. All right, this problem itself is too challenging, and even obtaining the data is challenging. So let's solve this problem, the initial data generation problem or human body measurement problem first, so that we can actually tackle the later problem. And our total capture paper is one of the output of our measurement step. So here we are interested in interacting multiple people, and we are also interested in measuring all these body signals at the same time. For example, facial expressions, finger motions, and body gestures. Because when we are using our bodies, these parts are extremely correlated. Some specific facial expressions should be very, very correlated to hand signals. And we want to find some rules humans are using when they are interacting. So capturing subtle details of entire body part is extremely important. But doing that is very hard, although we are using markers, because of all these occlusions, self-occlusions, for example, human have when they're moving their hands, for example. So our total capture paper is pursuing that direction, and it actually shows some meaningful kind of output in measuring all these parts at the same time.
One question I've got for you about this is, are the humans that are in this environment, are they just kind of naturally interacting, doing what they're doing, and you're capturing that and then kind of going back and labeling it maybe from, video or audio capture? Or is there a script that they're kind of working against? And well, I'll let you answer, then I may have a follow-up question.
Yeah, that's actually a very, very good question. Because although we collect people who have no idea about our project, it's very hard to ask them to do some natural motion, right? Because
then it's not natural.
Exactly. So for the purpose, actually, we are very closely collaborating with psychologists, and they are actually very, very careful about that. What we are doing currently is we build some specific social situation, and we actually define some social game, which is a kind of negotiation game. And this negotiation scenario where three people are negotiating each other. And in this game, which we call haggling, there are two sellers and there is one buyer. And the goal of this game is two sellers need to sell some competitive items to this buyer. And if the seller actually successfully sells the product within a minute of time, we actually gave some bonus for them. And because of this bonus, this monetary bonus, actually they can be really involved in this project, because actually the game itself is pretty fun, and actually they can additionally get this money. Because of the region, actually we found that their motion became very natural. For sure, because of the special system, at the very beginning when they first entered the studio, they actually see the cameras and they usually see the round. But we actually spend some time inside the studio so that they can be fully familiar with the system. And because we don't put any kind of camera in front of their face, because all these cameras are attached on the surface of the dome. So it just seems like some kind of special room. And after some time, actually the room is just somehow similar to other kind of room with some special wallpaper. So we found that their motions are pretty natural. And in the end, we actually did some questionnaire. It turns out the majority of people completely forgot that they are inside the dome and they get fully kind of involved in this kind of social game.
Mm. And so for labeling, have you perhaps in conjunction with your partners on the psychology side, have you developed a taxonomy of gestures or some kind of labeling system, or do you have a free description of the gestures, which I would imagine would be pretty difficult to deal with?
Exactly. So that's actually a really big question about this project, because let's say we can obtain all this body motion capture data from this, let's say, three people's interaction. Let's say we have all this facial expression movement and this finger movement and body movement. Then what type of problem can you actually tackle given this somehow restrict social situation? Maybe we can do some type of annotation, but actually annotation itself is some big question in this problem, because what kind of label can you annotate in this behavior? In computer vision, for example, there is this area named action recognition, but different from object recognition. Action is really hard to define because their starting time and end time is usually really hard to define, right? And making the label, the name of each motion, is also very challenging, because making the name means we wanted to describe the motion using some language. But language is in a very discrete space, and it's in a very low dimensional space, while the expression, the signals we are using in our social communication is actually really high dimensional space. So in that sense, actually, we don't try to do any so-called kind of annotational label. What we are labeling is kind of more objective thing. For example, who is the winner of this game? Who is the loser of this game? And for example, who is speaking at this moment? So that we can actually be very objective about the label. And our scenario is something like this. So how can we maybe make sure that robot is actually understanding the social behavior? That is another good question we should ask. And maybe our kind of solution for that problem is something like the following. So if a machine see the world, see the human's behavior, and if machine can predict the future motion of these people, then that can be maybe a way to define that robot has some understanding about our social behavior. More specifically, let's say we have all this data, and we somehow delete some humans' motion data. And can we actually can robot predict the person's motion? I mean, this hidden person's motion by observing the other people's motion. This is exactly the way we are interacting. For example, when we are interacting, we observe other people's signal, and we making some signal from our body, and the signal is sent to other people, and the other people are reacting to our signal. And actually, this is somehow the way we are doing communication. We just generate some signals using our body, send that. The signal is understood by people. And that is also, the reaction is also sent to us. And we are just exchanging some type of signals. And we wanted to do the similar thing for the machine. So machine is in the loop, and machine see the word. Machine decode the social behavior of other people, understand the meaning, and somehow predict the future motion. So this is a way we define the problem at this moment. And this is exactly what we are currently working on.
I'm trying to reconcile the idea that you're not doing any kind of annotation with the idea that you're able to predict motion. But I'm imagining you're not predicting the label of some motion. You're trying to predict motion itself. So, where is the hand going to be at some future time based on some set of interactions, as opposed to, what's the name of the gesture that the person is going to do?
That's exactly true. So we just use the motion capture data as the input signal for this machine learning tool. And output is also the similar types of signals. But based on the definition of the problem, we can consider different scenario. But one kind of scenario we are considering is the input is the other people's body motion, which is the motion capture itself, the signal itself, and the output is the target person's future motion. For example, if somebody is speaking something, maybe our target person can be nodding, which is synchronized to other people's behavior, or our target person would be maybe laughing or moving in a specific way. And actually, can we predict such kind of future motion of the target person given other people's body behavior?
Mm-hmm. And so does it work? How it sounds like a really interesting problem formulation. And tell us about the system and how well it performs, and then walk us through kind of how you build it.
Well, so that is something we are currently working on. And for sure, to this problem, we really need a lot of data because humans' behavior would be very different given the same situation, right? That would be maybe very related to our culture or personality. So given the same signal, actually, humans' behavior would be very different. So basically, it's multimodal. There exists this multimodality issue. And our data set is never sufficient for that purpose. So we really need to narrow down the scope at this moment so that we can tackle the initial problem. And you can consider this simple problem first. For example, let's say we are always considering three people's behavior interactions. And the input is two sellers' body behavior. So we have this skeleton, 3D skeleton kind of motion capture data of two people, two sellers. And those are the input of our, for example, neural network architecture. And can we actually guess the gaze direction of our buyer? So you can simply imagine that if somebody is speaking, if although we don't have any verbal kind of signals, if somebody is speaking, there could be some speaking specific kind of body behavior, and probably the buyer's gaze will be on this speaker, right? This is some very simple kind of scenario we can imagine.
Right.
So this is just one channel, just estimating the gaze direction of the target person. Can we increase the dimension? For example, what about the facial expression? Facial expression is indeed some 3D face key point, or we can just simply imagine the mesh itself. So we have all these vertices moving 3D meshes, and this itself is the output of the network. And can you actually predict the target person who is the seller, a buyer in this case, of the buyer's facial expression based on the other people's kind of behavior? Or another case is maybe location. Where is the location of our target person? Because basically humans try to have some distance among each other. And this distance is also somehow trained throughout our life. And we actually maintain some specific distance when you're communicating. So actually machine can predict the distance of the person, target person, and orientation of the person. So this is something we can imagine as a very low dimensional signal. And we can actually consider higher dimensional signal. For example, can we actually predict the target person's skeletal movement or long-term movement or hand gestures? But at this moment, all this part is still remains in a very challenging problem because we don't have any specific output in this case. But this is basic focus of our purpose, our motivation.
Got it. So the big picture is understanding how to predict from these 3D motion capture models human behavior in interactions so that ultimately machines could better understand human behavior and make predictions based on it. The longer term goal to get you there is being able to predict on a, say, pixel by pixel basis what the future state of one of these participants' body position is. But the intermediate steps or the near term challenges, and that's really, I think you sensed that was my, what prompted me to ask, is it working yet? That sounds like a huge problem, and it is. So the way you're tackling that is these intermediate problems of, can we track the gaze direction? Can we track the facial expression? Can we track hand position? Things like that.
Exactly. So basically, our current kind of problem definition is we want to make a machine to understand the human's behavior. And the way to do that is making some system which can predict the future motion of the target person. And there we can imagine some simple, good examples and application for this. For example, let's say we have this AI kind of Amazon Alexa or Google Home kind of AI system, which is nowadays just using verbal language, for example, audio or speaker. But let's say this small machine has video as well. So it can capture the scene, the human's behavior using camera, and actually it can display some behavior using their own display. I think this can be really interesting because now somehow they can understand the meaning of our body behavior and they can react with that. You can also consider many interesting AI system or robotic system. For example, if there is just a toy robot which is actually interacting with child, and if the machine can understand the meaning of the child's body movement, basically let's say the baby cannot speak at all, but it can actually make some facial expression and so on and so forth. But still, maybe machine can understand this because human can do that. Mother and father, they directly know the meaning of some specific movement of this child. So this can be also interesting application. Also, you can imagine some application in medical area. For example, we have all this surveillance system, and we need to maybe monitor the elder people's body behavior so that we can somehow identify some unusual kind of behavior. For example, in this case, all this measurement kind of skills and techniques and this understanding their behavior would be extremely important kind of techniques for these applications.
And so in the total capture paper, what you're presenting is a deformation model for tracking these face, hand, and body positions. What do you mean by deformation model?
So basically, we can do some 3D reconstruction without multiple cameras because Kinect can do some type of thing, or depth camera can do some type of 3D reconstruction. Here, deformation model basically means the human's behavior is parameterized by some limited amount of parameters, and this parameter represent body motions. So body motion means each joint angle is one parameter for each joint. So we can consider some number of joint, and each joint, let's say, has 3-dimensional rotation vector. So that is some parameterization for body model. And also we can do some parameterization for shape deformation. So we have, let's say, 10 parameters. And by just changing these parameters, we can represent the different size and shape of the people. So without this parameterization, actually reconstructing 3D human is more challenging because maybe we need to reconstruct all this vertex, all this 3D point of all this entire body. And that dimension is extremely large. For example, let's say we wanted to reconstruct some mesh model for each individual. And let's say this mesh model has, let's say, 10,000 vertices. Then basically we need to estimate the location of these 10,000 vertices for each time instance. But the interesting thing is our surface is extremely correlated to each other. So our vertex is not moving arbitrarily. If we know some location of one part, we can easily guess at the location because they are somehow very, very, in a low dimensional kind of space in the end. So this parameterization is basically to parameterize all these variations of human body motions and body shape in a low dimensional space, but still we wanted to have some sufficient expressive power to express all this body behavior and the shape deformation. And our total model capture is basically, so this deformation model is actually really popular area in computer vision and computer graphics, and there exists really popular deformation model for body and faces. Our major contribution of our paper is we build a model which can actually include all these parts together, including body deformation, body motion, facial deformation, facial expression, and finger motion and finger deformation, and so on.
And when you say you have built a unified model, in what way is it unified? Is it, have you built some ensemble that does each of the things well, or have you kind of abstracted away from the individual parts of the body that you're modeling and really trained a model that can, given any of those inputs, produce an output?
So in this paper, actually, we defined two different models. The first model is more related to some independent models. For example, we have independent facial model and body model, hand model, and we somehow consolidate together by attaching each other explicitly. So this model is called Frankenstein or Frank because the way we built this system is very similar to this Frankenstein's model. But yeah, the problem is all parts have individual parameterization, so sometimes they are not consistent to each other. The final model we built, which we call ADAM, has single parameter space for entire a shape space. So if we change one parameter of this space, a face, body, and fingers are changing together. And basically defining this low dimensional deformation space means we wanted to find out some correlation of different parts so that we can reduce the dimension of this space. That's the key. And since we build this model by collecting all this 3D reconstruction of body, face, and hands together, actually, when we build this model in a low-dimensional space, the model somehow knows the correlation across bodies. For example, if somebody has really big maybe face, maybe their hands would be also big as well. And by somehow merging this deformation space together, somehow we can reduce the space. So the final model actually has such kind of ability. So it has some amount of deformation space which can control all this body, face, hands together. And also all this motion body motion space is in a single skeleton space. And that means so hand cannot be apart from the body, and we know they are somehow linked together by a skeleton, which is quite important for computer graphics area, for example, retargeting and so on. So yeah, that's the meaning of all this total body motion capture and deformation model space.
And so is the idea that you were expressing it with the dimensionality reduction with the Adam model that, with the Frankenstein model, these the body parts are, more closely related. We understand that if, as you were describing earlier, if we create a mesh model of the face, if, the vertex in the cheek moves, then the vertex in the eye is probably going to move. Like with these relationships are relatively easy to understand. But on this Adam model, you've got the single parameter space, and so moving a parameter may have implications in multiple places, and so it's more challenging and requires a different approach than you might take in reducing the parameter space on the Frankenstein side or on the kind of ensemble side. Did I capture that correctly?
Yeah, mostly. So basically, the reason why we built this Frankenstein model is actually to build this ADAM model. So, for example, for dimension reduction, we can simply use PCA kind of method. But the input of this PCA model is basically the 3D mesh model of many people. So different shape and different body pose. So that actually this PCA can learn the variation space of this humans of deformation and motion changes. But generating such input, the mesh data, which include all these details of face, body, and hands, making such reconstruction itself is challenging, although we use many cameras, because we are interested in subtle movement of facial expression, and we are also interested in this subtle movement of fingers. And at the same time, we are interested in this large movement of bodies. So how to place the camera is actually a big problem, because if we want to capture the face, the camera should be very close to the face. If we want to capture the detailed hand, maybe people wanted to use the camera, which is very close to this finger. So doing this reconstruction to build the ADA model, the reconstruction itself is challenging. So we wanted to make some intermediate status by using some already available 3D mesh model, deformation model. And that's the main kind of motivation of this Frank model, which is easier to build without doing any PCA kind of learning. And after we have this model, actually we use this model to reconstruct all these details together. And then finally, we reconstruct like 100 people's shapes and body motions. And in the end, we just put all this to this PCA kind of tool so that we can actually learn the deformation space. And there are just actually two big regions of doing that. For example, if we build this deformation model for entire body part, actually we can use that in the more challenging situation. For example, now let's say we don't have this multi-view system. And now we have this single image or videos from maybe YouTube or internet. And let's say our goal is similarly to reconstruct this 3D body behavior, body motion of the person. This is obviously extremely challenging problem because we now have single view and we wanted to get this 3D motion capture data. But since now we have some model which restrict the space, the search space to this low dimensional space than the original high dimensional space. Actually, the problem can be much easier because now what we need to do is just estimating the parameter of this model, which can express our measurement, which is the image. So the major the main motivation of research is this total capture is after we build this model, now we can use this model to do this motion capture, face, body, and hands motion capture in the wild situation, so that we can collect more and more data in this challenging situation. So that is the major kind of motivation of building this parametering model. And another big reason is once we have this parametering model, actually the data structure can be very simple. So instead of having, let's say, mesh structure, which has some arbitrary number of vertices, now we have some fixed amount of parameter to express the particular motion of the person. So now we can consider these parameters as the input of our machine learning tools. That can be the input. So other people's motion is abstracted as a parameter. And then the machine learning tool produces some parameters as the output, which is actually representing some motion of the target person.
Can you comment at all about the size of the parameter space relative to the size of your typical 3D vectorized or mesh type of model?
Mm-hmm, mm-hmm. Well, I don't remember the exact number, but the rough number is we have 21 joint for the body, and each hand has 21 joint, and each joint has 3-dimensional space. So 21, 21, and 21, and that is 63, and each joint has 3 dimensions. So that is for the motion to represent the body motion. And we can also have facial expression, and facial expression is not explained by this skeletal movement, that is explained by another parameterization, which is expressing the movement of this mesh structure, and that has 100 dimensions. So 100 dimensions for facial expression, and about 200 dimensions for body motion. And we have about 40 dimensions to represent this shape. So by changing this 40 dimension, the shape, the size, and the shape of the bodies are changing. So that is more or less, I cannot sum them up now, but about 400, 500 dimensions to represent the human's behavior, including face and body and hands. But the original dimension can be probably, if we don't have such kind of model, let's say we wanted to do the similar thing by a mesh structure, and then the mesh we are using is around maybe 10K vertices. So each vertex has 3 dimensions, and that is about 30K dimensions. So we reduce the 30K to this 500 dimension to represent a similar thing.
When you look at the skeletal skeletal model plus the face, you have several, like 100, 100 or so, 120, 130. Then you said you can reduce that down to 40. And then you said, then you started saying 400, 500. And I didn't catch where the 400, 500 came from.
Okay. Let me try to explain this again. So if we just consider skeletons, which is kind of a stick figure, then we forget about all this surface movement. So we can consider the joint location for the body, joint location for the finger, and some surface key point movement of the face. So each point is a 3-dimensional space, and we can maybe consider all this number of 3D key point. So that is a way to represent the human body. But let's say now we are more interested in the subtle details of the surface. That means we wanted to get the mesh as the input and output of our machine learning tool. And in this case, now instead of just handful number of stick figure joint location, now we consider all these vertex locations of the surface. So that is around, let's say, 40K dimension. Because to represent some details, we need many, many vertices. So the way to reduce this is, instead of having independent vertex separately, now we already learned the correlation of all this vertex movement, and we can reduce the space by using the motion space and shape deformation space. So motion space means we just keep the similar motion parameter for each joint, which is similar to stick figure. And shape deformation space is actually catching the variation of the surface of the given fixed body motion. So by changing this deformation space, actually humans' surface shape can be changing. And by changing this motion space, human can behave some body motion. So this shape deformation space is about 40K. About 40 dimension, which is really extremely low dimension,
Right.
because human bodies are very, very, very correlated in this case. And for motion space, we have 3 degrees of freedom for each joint, and we have about 60 or 70 joint. So that is about 200 dimension to represent the body motion. And also we have about 100 kind of dimension to express facial expressions.
What you're able to represent with this lowest dimension, the lowest dimensional vector, this 40, is not just the stick figure, the body positioning, but also the surface as well. Is that correct?
Exactly. So we have a function to convert these parameters to the original mesh space. Mm-hmm. The function is somehow fixed function. So given this parameter space, parameters we obtain, we can convert that to this mesh space. So instead of keeping the mesh space, we can just keep the parameters. The problem obviously here is the expressive power of this model is limited. So for example, usually in nowadays, this model can express some some body shape with minimum clothing, because modeling this clothing is extremely challenging because of all these variations we have. So usually when we build this model, the input data is limited to somehow subject with minimum clothing. Because of the region, this model can express only the mesh with minimum clothing. For example, if you generate any arbitrary body shape and motion from this parameter, the output is almost always this kind of naked body with minimum clothing.
You've reduced the dimension down to this 40, and then you're able to use this 40 to produce, you said you refer to it as a fixed function. Is this a function that's learned through a machine learning model, or where does that function come from?
This function is somehow, it's actually a very common function in graphics area. So actually, from the motion capture, if in graphics area, from the motion capture data, which is basically the 3 degrees of freedom for each joint, we can manipulate, we can animate the 3D character. And actually, the 3D character output is mesh, although the parameter input is this motion parameter. Similarly, we just use the similar function, which is called linear blending skinning. So we have some mapping between the vertex movement and the skeleton movement. And we are just manipulating this skeleton. And then as an output, we can get the location of each vertex of the mesh.
And so you've developed this representation of the body. How does this tie into the larger goal?
Yeah, exactly. So first, we wanted to parameterize all this face and body and hands movement in a common format, a common motion capture format. That was one of the reason of building this model. And as I mentioned, the final goal is actually to use this model to get the similar motion capture output in the YouTube video. So actually, we are working on this project, and now the goal is instead of having multiple views, we will just have a single view, single YouTube video, and we wanted to get the motion capture of the target person. And motion capture output has all this component, face and body and fingers together. This is ongoing research, and we actually get some meaningful result at this moment, and which we plan to submit that to a conference in the end. So basically, we wanted to convert all of our collected data to these types so that we can actually put this to our understanding part. That is the current one at this moment we are working on.
And is PCA the primary place that machine learning is used in this project, or there are other places where you're building models as well?
Well, actually, this project is a little bit far from the popular machine learning area. This is more like a 3D construction. And in this paper, what we show is usually this finger reconstruction and face reconstruction and body reconstructions are considered as separate problem. But we actually somehow demonstrate that we can capture all these components together without using any markers. And to do that, maybe one of the key kind of contribution is we use this 2D key point estimation method for each individual camera. And in the end, we combine them together in this 3D space using multi-view system. And in the end, this 3D key point we reconstructed by using this 2D key point detector. It turns out they are working extremely well in this challenging problem, and we just show the result as the full total body reconstruction result. So in that sense, probably it would be good to share the 2D detection, post-detection problem our lab is working on.
And that is the open pose work?
Exactly. Yeah, exactly. So this 2D body pose detection area is a very popular area and one of the most successful areas in computer vision in recent years. So now we have really great algorithms which can detect this human's body key point, multiple people's body key point in YouTube video and single image. And OpenPose is a version of that. And one good thing about OpenPose is this is providing all these facial key point and body key point and finger 2D key point in a single framework in real time. And multiple papers our lab has been presented is included in this work. And actually, this is closely related to our Panoptic Studio project because we are using this detector to reconstruct all the total motion in the end. And at the same time, we use our system to generate new annotation set to train this 2D detector. So this is, I believe, a very interesting idea because usually this multi-view system has been used to reconstruct 3D. But now we believe this multi-view system can be a way to generate some 2D annotations for 2D detector because sometimes this generating 2D detector itself can be challenging. For example, let's say this is one paper we published in last CVPR, and the goal is to make this 2D hand key point detector, which is now the part of the OpenPose. And the main idea is very simple. We just wanted to make some data set for 2D hand key point detector, but just annotating this 2D hand key point is a challenging problem because of all these self-occlusions. So at the beginning, we hired some annotators, and we asked them to annotate this 2D key point given some 2D image. But it turns out usually these fingers are occluded each other, and just clicking this finger key point is a challenging problem. And our idea is, all right, if we can capture some data in this multi-view system, since we have 500 views, let's say we wanted to capture some finger movement. We wanted to annotate some key point of some finger movement. Then since we have this many views, we can easily find some good viewpoint to easily annotate the target finger part. More importantly, if we can have some 3D reconstruction of the target hand, if we can project this 3D hand to 500 views, each individual viewpoint can have a new annotation by projecting this 3D hand to this single view. And we just use this annotation for a neural network architecture to train the 2D detector. It turns out this is extremely successful in making this 2D key point detector, hand key point detector.
So in a way, it's kind of a specialized mechanism of data augmentation.
Exactly. Yeah, that's exactly true. But in this case, we can use this multi-view supervision so that we can filter out some noisy outputs. For example, since the original target hand should be in the 3D space, and our image is just capture of the 3D space in this 2D space, so ideally, if we can generate some rays from each individual camera, they should intersect in this 3D space, which is the original 3D joint location. If they are not, then we can simply say that maybe the detection or 2D measurement is wrong. So we can easily filter out all these noisy cases using this multi-view supervision. And that is the key to make this data augmentation. Yeah.
Awesome. Well, Han, thanks so much for taking the time to share this with us. Are there any final thoughts that you'd like to share to kind of close us out?
Yeah, so currently we are trying to release entire of our data set we generated from our Panoptic Studio. So people can easily download 500 videos for the same input. And also they can get all these 3D annotations we generated, for example, 3D key point and also depth information or this 3D point cloud for the same target scene, so that we believe people can use this kind of data to many interesting computer vision and machine learning problem, because people now have some 2D image input, and they can also have corresponding 3D annotations, and that can be maybe interestingly trained in many interesting machine learning techniques. For example, given the single image, can we generate 3D skeleton? Given the single image, can we generate depth data or 3D point cloud? Because we all captured these all different sensors output using hardware synchronization and the calibration. So this can be easily kind of maybe not easy, but this can be in the end used for many interesting machine learning problems.
Oh, wow. How many images or videos are you including? Not how many unique kind of scenarios or captures are you including?
So the original data is about 10 hours of many different situations. So we have captured some musical instrument like playing piano, cello, and so on. And we also have many social motion capture results, for example, three people interacting. Also, we have captured some very simple example like range of motion, which can be easily maybe used for much easier kind of problems. So yeah, and we keep collecting more and more data, and we try to release all of them in the end.
Awesome. Well, once again, thank you so much, Han, for joining us.
Thank you for having me. Thank you.
All right, everyone, that's our show for today. For more information on Hanbyul or any of the topics covered in this episode, visit twimlai.com/talk/180. If you're a fan of the podcast, we'd like to encourage you to head over to your Apple or Google Podcast app and leave us a 5-star rating and review. Your reviews help inspire us to create more and better content, and they help new listeners find the show. As always, thanks so much for listening, and catch you next time.